I will talk about the kinematic and non-linear regime of turbulent dynamo, and mainly to show some phenomenological relation for this processes, and also I show some results, numerical results, which prove this relation using the shell model approach. And I think it will be a good idea to give additional explanation to what we should get from Peter Frichtol to tell you about what is a shell model, and then I shortly describe which model we used and present some numerical results. Sorry? Yes. The motivation of this work, we have the motivation from this work being on the similar MHD program in Brussels last year, and we realized that there are a lot of misunderstanding between experimentalists, geophysicists or astrophysicists and people from direct numerical simulation about quite simple features of turbulent dynamo. And the idea was to present the picture about this as clear as possible with in the simplest way as convenient for us it was. And I think the possible reason for this misunderstanding was because of everybody have in mind this couple of MHD equation and knows meaning of Reynolds number, but almost everybody works in different area on this plot. Here the hydrodynamics Reynolds number, and here the magnetic Reynolds number. And if we look where is the experiments, oh sorry, it is here. Dynamo in the Earth or another core of planets is another part of this plot. The Sun is here, the galaxy and accretion disk is also in a different place, and all numerical simulations, direct numerical simulation, mean almost in this corner. So you see, it's a lot of possibilities for misunderstanding between all this. It depends where you are. So, and what we propose that the shell models can be helpful to cover more or less all this area in some sense, and you will see how it looks like. So, I would like you to switch from understanding of MHD, evolution of MHD system, thinking about Fourier mode triads exchange. It is quite a general result. It's that all interaction, nonlinear interaction, appear in the triad exchange by energy and by helicities. And there are only two types of triads, possible triads. It's triads only three Fourier modes of U can interact, or two magnetic modes can interact with the set kinetic modes. And the rule which must be satisfied always is this triangle rule that the sum of wave vectors must be zero.
Excuse me, Radion, but another possibility, interaction between one magnetic and one hydrodynamic with third magnetic.
Two magnetic and one hydrodynamic.
Magnetic, hydrodynamic and magnetic.
But it's you see, it's triad. It doesn't matter. So it depends. Just only show that there are two types of triad where the magnetic or kinetic or energy can be redistributed, or helicity can be redistributed. For example, the kinetic helicity can be distributed only inside these interactions. I mean in conserved way, to be conserved. But magnetic one is only in this interaction, is conserved. So it's quite convenient to consider, to think about the nonlinear dynamics having this picture. And what's happened if we use these rules? Let's consider three vectors k1, k2, k3, which satisfy this law. And then, as you remember, the shell model approach use the Fourier space is divided in shells, and we average energy inside this shell, spherical shell. And let's assume that for the given shell Sn, we have k1 in this shell. For the shell Sp, we have vector k2. And then let's calculate the probability that vector k3 will belongs to shell Sq. And this conditional probability is plotted on this histogram. And you can see that the white squares shows the area where the shells cannot interact at all in any dynamics. So let me explain again. So you see the number of shell P, shell Q, and for the given shell N. And what we see here, it is local interactions. So what it means that P is only N plus 1 or N minus 1, and Q also N minus 1 and O N plus 1. So interaction mainly is local. But there are these lines, three directions, which correspond to the non-local interaction and correspond to non-local energy transfer or non-local helicity transfer or something or whatever you want. So it's a quite general picture. It's true for any case, and we use this structure of interaction to construct the shell model. Here's some additional information. I would like to summarize in the way that you understand that we lose, if we play with the shell model, we lose all information in real space because it's Fourier decomposition, and we forget about the phases. Also, we lose the information about direction inside the shells because we make averaging over all direction. We keep only the length of wave vector. So it means that we lose all possible, we lose features corresponding inhomogeneity or anisotropy. But we still keep the proper energy transfer between shells, energy and helicity balances between different scalars. We can have a spectra of fluxes in Fourier space and the time dependency of fluctuations. Of course, we do this in order to gain the more simple ordinary differential equation, which can be solved with pretty nice statistics. And for such set of equation, we can take the very high Reynolds number up to we can consider up to 10 decades of scales. Yes.
But if you lose all that, what fate will you have in what you have?
We will have a distribution of kinetic and magnetic energy in Fourier space. Just only energy. We don't know about the phases.
All that information on, let's say, anisotropy,
yes.
phases in a shell.
Yes.
If you lose all that, how do you trust what you get for your energy transfer?
Because
check,
yes, we can just maybe I will finish. I will just we make the averaging over ensemble, but we keep the energy balances and helicity balances. and it gives us proper fluxes of energy or helicities. So they interact not because of it is 3D vectors, but because of this structure of interaction. So we took this knowledge to constrain the exchange of energy and helicity between shells, between different scalars, and we satisfied. I shortly why we trust, because we use more or less first principle. Of course, we cannot check it directly. We can take this model, make a simulation, and compare result with known result for pure hydrodynamics or for magnetic, for MHD equation, and so on. And if we find some discrepancy, we will say, okay, it's a bad model. But still, there is no strong discrepancies between direct numerical simulation and a result which we obtained from shell models. This is why okay, yes.
For 10 decades, do you need approximately 24 shells?
Oh, the number of shells, it is not important. Okay, it's 20 or 80 shells, or maybe 100 shells. It's not
8 shells. 8 shells. You need 8 shells, right?
It depends on the lambda. Lambda is the ratio of between neighbor shells. And the principle how it constrained, you see, this is a question for shell models. It looks like the original equation, Navier-Stokes equation, where we have advection term, Lorentz force, diffusion, forcing. For induction equation, it's also two terms for quadratic term for nonlinear interaction. A and B, small a and B, it's a coefficients, unknown coefficient, but fortunately we can define this coefficient from the conservation law. It's only one solution is possible. Okay, the main the families of different shell models is due to different representation of these non-linear the quadratic terms, and we used all possible interaction where different shell can be interact. So it's all possible non-diagonal triad interactions. So this is model we used for simulation.
Do you follow U and B, or do you follow U and B directly?
Yes, it's UN square is the kinetic energy at given scale, and Bn square is the magnetic energy.
What are you following in your simulation? UN squared or UN?
UN and Bn. It's a complex variable.
Okay.
It's a complex variable. Of course, if it will be scalar, we cannot define the helicity and magnetic energy. But if it is complex, we have two variables indeed for each shells, and this is why we can define the energy and helicity.
And one shell is a
spherical shells, which is a range, it's a shell, it's a thick shell, which and it contains all fluctuation with the length of number. Sorry.
And for this shell, we have one complex vector.
Yes, not complex vector, it's a complex scalar. And the meaning of the scalar, the square is the energy of fluctuation. And the face of the scalar gives us the helicity. In some sense, it's definitional. So we need at least two variables for U to define the energy and helicity. It's a minimum.
If you would go to the real 3D picture, and I guess you
cannot.
Then you would have a vector which is perpendicular to your shell due to divergence equal 0. So you threw away the direction of this vector. Right?
It is not direct transformation between 3D and this scalar components. We cannot reconstruct the distribution in Fourier space, in three-dimensional space.
Sure, but in real Fourier space, we have all these modes interacting, and sometimes these vectors are aligned, and sometimes not.
Yes, sometimes not.
When you do your coupling, you must make an assumptions about what is their relative orientation. So do you just assume they are randomly oriented in white noise?
Yes, but we prefer to decide that we already lose all directions, and we only satisfy conservation law. Just it's only one law which we try to satisfy. We don't think about the direction. It's parallel or perpendicular because we have no directions at all. It's a way of construction. But there are the papers of Zimin and in 1998 they used the wavelets decomposition of original three-dimensional vector fields, and they show that taking this decomposition and after the averaging of the equations, you can finally obtain similar ordinary differential equation. But of course, he took some assumption about the correlation and distribution about vector, about directions and okay, about everything. So
I mean, just
usually it is
for clarification, I mean, such a model can really not have much realism in it. This is well known, and these models have been studied since the 70s. So the only reason why they still continue to be studied is because, for some strange reason, they are indeed, for certain aspects, useful. And I think that's the main thing we have to think about. So as far as spectra is concerned, and possibly also the relative spectra, much of this does not, and indeed also intermittency, because they of course have also time dependence, intermittency corrections. As far as those aspects is concerned, they only depend on the fact that you do have something which has to do with large range of wave numbers, and that certain conservation laws are conserved. If you change the conservation laws, for example, from 3D to 2D, for example, you will recover exactly what you would expect. So I think it's rather this aspect which is just so amazing, and therefore, since the 70s, such an incredible model continues to be useful every now and then.
In science last year also we find out, which is incredibly correspond to the direct numerical simulation. I will show you this result. But yes, it is long story about the shell models. There are several reviews and possible justification and many, but just maybe it is too short, not so many times.
And attempts to make it better make it typically worse.
Yes. And just only one, I would like to note that there is one term which is important. Indeed, it's a factor which controls the strength of non-local interaction. This power of this K, this Tm, it's really the ratio between two scalars which interact. So it means that if the alpha is negative, then more distant scales interacts weaker, closer scales, neighbor scales interacts more stronger. So, and for isotropic homogeneous turbulence, it was shown it should be about -5/2. But for anisotropic, or especially if there is some correlation between the direction of magnetic field and velocity field, then it can be different, and we check out it's true. So I start with the result, and the picture which we wanted to obtain, it's not the picture, it's some movie, and you can see. So we start. It's a Reynolds number 10 power 7, magnetic Reynolds number 10 power 8, and we start with a fully developed kinetic energy spectrum. So there is already fully developed hydrodynamics turbulence and very small level of noise for magnetic field. And what we see at the beginning, it's energies, and this is the growth rate of magnetic field for different scales. And we see that at the beginning, all scales start to grow with the same growth rate because they correspond to the same eigenmodes of magnetic field. And when we start simulation, it looks like this. Magnetic field is appearing sometimes it is not for somebody it is not clear why it's really appear at smaller scale, and this smaller scale, as you will see, it's near the viscous ohmic diffusion term. Oh, the ohmic diffusion scale. I will continue. So now you see the kinematic regime is finished, and this scale is about the saturation. And what's happened here, these larger scales continue to grow up with the constant, the same growth rate, but the rest of spectrum does not grow up at all, because they are almost saturated, because this scale is saturated. Yes? Oh yes, 5 minutes. Then we can see what is following we obtain, and namely this regime, the way to the full saturation we would like to describe in some phenomenological way, because it looks like, okay, I will show you again. It's like a scale by scale saturation scenarios. The talk was we proposed some scenario for this saturation way, and okay, let's look. Okay, Kolmogorov ideas gives us the spectrum for kinematic energy. We can estimate the viscous scale, which is appear when the quadratic term is the same as diffusion term. We can obtain the k nu, which is the dissipation scale of kinetic energy, is scale as nu minus 3/4, and known picture is like this. Here the scale where I inject the kinetic energy, this is dissipation scale, and very pronounced inertial range. I put all magnetic energy spectra on the same plot, and now what we see that there is the scale where the magnetic field has the maximum, and then it's propagated to the larger and larger scale. We estimate the local magnetic Reynolds number, and it is 10 power 4 for larger scale, and it is about 3 for the scale which has the maximum at this in this spectrum. And we understood why it is about 3. So it looks like it is a minimum magnetic Reynolds number for turbulent dynamo. Okay, here we wrote the induction equation and the condition for the dynamo. Then this stretching term is larger than diffusion term, and we know that the turbulent dynamo appear in the shear, and this is the scaling for the shear. We see it should be k power 2/3. And for small Prandtl number, yes, it was the case we considered before. It was for small Prandtl number, the ohmic diffusion scale is smaller than viscous scale, and dynamo is mainly local. So this shear produces the local fluctuation of magnetic field. It's shown here. You see the maximum of the spectrum is a bit larger than this ohmic dissipation scale. And we can calculate the scale, I mean K max, having this simplification of induction equation. If we simplify this, you see we obtain this simple relation for growth rate. So growth rate, which depends on kinematic growth rate, depends on us. There are two terms. One is due to shear, k power 2/3, and another one is dissipation, which is k power 2. And of course it's a parabola which has a maximum. So when we easily define the k max and corresponding gamma max. So this is this distribution of kinematic growth rates which we used. So we check out the scalars, proper scalars for growth rate, maximum growth rate, and this maximum, the corresponding scale. and it's a result of the simulation. You see that growth rate completely independent on viscosity, and it is scaled as about like this, about -1/2.
Sorry, it is independent on magnetic diffusion.
No, it's independent on viscosity.
Kinematic viscosity?
Yes, yes. And it scales very properly corresponding to our phenomenological relation. It scales as diffusion, magnetic diffusion coefficient. So it's you see, it's for different Prandtl number, it is almost the same. Okay, maybe this is very it's too close to unity. This is why there is some deviation here.
So what is the threshold for excitation?
It's we show that
In
it's
magnetic
about.
Reynolds number.
Oh, we don't care. We are not interested in the threshold because we consider we want to consider the very large magnetic Reynolds number. But if you want, it's another story about threshold. But if you want to know it, I already told about it was here. Sorry, in the wrong direction. So it's about 3. So you see, we can calculate the local magnetic Reynolds number. And we find out that the magnetic field the peaks about this scale where the magnetic Reynolds number is about 3. So it's another way to think about. So we can define the threshold for each shells, and we see that magnetic fields start to grow if the K max, that the magnetic Reynolds number at K max is 3 or larger. Okay, it should be 3.
But this is in contradiction with direct.
Can you give it to the discussion?
Yes, it's a pity because so next what I would like to show that it's a time dependence of magnetic energy for different shells, and you see that small scale shells at the beginning they grow exponentially, and after this shell is saturated it starts to grow slowly. And this is I will skip just explain the scenario which we suggest and the result which we obtain from this scenario. So we assume that at some moment the magnetic energy at scale K is saturated. So it means that energy reach the kinetic energy. It is more or less. Then we consider the neighbor scales, which we believe continue to grow up with kinematic growth rate. So we can, having this scaling, we can estimate the level of B at scale K plus delta K. Okay, no problem. And then we can say we can calculate the growth rate, kinematic growth rate for this shell. Because we have this, we already calculate this this dependence. After that, we know that this shell must saturate. This shell must saturate at level which is UK plus delta K at time delta T plus delta T. That's mainly all what we need. And then, yes, it's a condition of saturation. And then finally, if we take the limit of small delta K and delta T, we obtain this differential equation, which is the K. Here K is the largest scale where we observe the saturation. So, taking this quadratic relation for this, finally we obtain this result that K, depending on T, is scaled as T in power minus 3/2. It can be inverse, and then what it's really the result is that inverse of growth rate is proportional to time, starting from the time where the saturation appears at the beginning. Okay, the picture also, another thing, you can see what interesting feature that after this scale is saturated, the dissipation scale, so it was previous spectrum for kinetic energy, but after saturation, the scale, viscous scale is changed. And it is obvious because of energy which comes from large scale to smaller scale, flux of energy was reduced because some part of energy transferred to the magnetic energy, and magnetic energy disappear locally because of dissipation. This is why this scale is getting smaller, because the flux of energy, kinetic energy, at this scale is getting also smaller. And we compare our phenomenological relation with what we observe with the shell model, and we really see this scaling at some range of time. This time corresponds to that smaller scale saturated. This is about the largest scale more or less saturated. So we see it's not so pronounced here, but for large Prandtl number it will be more pronounced. Here there are some comparison with Dirichlet numerical simulation. It's really amazing in good K-max. We calculate K-max for different results for Dirichlet numerical simulation. It is exactly correspond what we obtain in phenomenology and shell model simulation. Just moving for large Prandtl number, because it's also interesting things. Now also we start from developed kinematic. Yes. Okay, I will show only this movie, and then if it's somebody wants, I will explain in details. So it's a fully developed kinematic energy spectrum, but now viscous scale is expected much smaller or much larger than resistive scale. And what we can see that magnetic field is growing at the range, more or less in the some range of small scales, and then it starts some saturation like this, and also we see the reduction of growth rates at smaller scale after saturation starts, and the magnetic field propagates to the largest scale. Okay, I have some justification of what's happened here. Also we calculate the growth rate for this case, and so that's a result we obtained from simulation. You see here much more pronounced this range of time where we have the scaling. I mean the scaling, the inverse growth rate during the saturation is proportional to time. So it's exactly what we observe. And our suggestion for people, for everybody who can do this, who can calculate this growth rate at this saturation regime, just check out, is this true or not? So with really what we assume that growth rate change as a minus growth rate square. So I think it can be checked out somehow and compared with the Dirichlet numerical simulation. So unfortunately I had some results which is interesting to compare with the large scale dynamo model, where the transport coefficient are fluctuating. Also we use the shell model to produce the fluctuation of the alpha or beta, and the result was quite interesting. Thank you very much.
Just one question.
Try to compare your results with the results obtained with the delta correlated entire velocity field. For example, it's possible to compare the threshold for excitation of magnetic equations with the magnetic nodes number. And it's possible to compare scalings of the growth rate with the magnetic nodes number, which is the square root of the magnetic nodes number. Is it possible to...
I'm not sure, because this velocity field is not delta correlated.
Yeah, I understand, but numerical simulation, direct numerical simulation by Shikachikin also showed that the threshold of excitation of the order of the value which is predicted by the series delta correlated in time velocity field, for example, our predictions and also predictions by Catania and
yes, I remember we compared all these results in our paper about threshold for small Prandtl number.
Yeah, I speak about the small.
Yes, we check out and we find out But we can go much deeper. I mean, we can consider much smaller Prandtl number, and we find out that it's saturated. The threshold is saturated.
Yeah. Okay, saturated state is possible to compare only with DNS.
We can discuss further. You had a question? You had a question.
The A is never 3/2. The Kazantsev slope. You don't get a Kazantsev slope.
No, no.
That's my slope.
No.
Steve?
I was interested in the result you had for the scale of the field that you get in your Angular function. You had it was the one with Rm looking like 3, Rmk was 3. So have you made any assumption about the correlation time of your turbulence? Because if you make the assumption that the correlation time is quite long compared with the turnover time, then you can derive a kind of similar result. Magnetic Reynolds number should be equal to 1. On the scale of the eddy that's doing, without making any assumptions about shell numbers.
Just what I know exactly, but we calculate the correlation time for each shells, and we find out it is exactly as it goes as the turnover time. The scaling is the same.
It's the same as the turnover.
Yes.
Okay, let's thank Florian.
Said that he doesn't have this k to the power 3 house, Kazantsev spectrum. You do. You were just misunderstanding. K to the 3 house. You doesn't do that. Oh, you probably understand why it's 3 house. Like
Minus.
Yeah, but you had it in the plot. It showed
but
plus
it is
2.
not exactly. It's with some intermittency. It is more steeper than.
Yes. And you had, but you showed a plot or a sketch perhaps where it was plus 2.
Oh, it's about plus 2. It is not Kazantsev. Why do you think it is a Kazantsev?
plus 3 house.
Yeah, but you said 2. Plus 2.
Okay, we find out the same result in the paper for this spectrum, which is where little numerical simulation was done. Okay.
So now, we have Sergei Nazarenko, who is going to talk about MHD turbulence in a box.
Okay, thank you very much, the organizers, for inviting me to speak at this workshop. Essentially, so we'll be talking about, I'm going to investigate the effect of a finite size occupied by MHD turbulence onto its properties. So of course, there's plenty of physical situations where size the volume occupied by MHD turbulence is finite, as actually, shall we say, 100% of situations, right? There isn't an infinite system in reality. But of course, the question is how big, how does it matter, right? And my model I'll be talking about will be based on a reduced MHD equation, which, if written in Fourier space for Alsacer variables, can be written like that. So with some interaction coefficient here. So I already used interaction representation variables so that in linear approximation these variables stay constant, right? And as a result, I have here fastly oscillating coefficient in the nonlinear term, which is due to the Alfvén waves. Okay. So this what we have in the exponent. This is the difference of 3 Alfvén wave frequencies. So now, how does the finite box enter into the problem? Well, finite box means if I'm using periodic boundary conditions, my Fourier space is discrete, right? And I know that if my if nonlinearity is small enough, the leading nonlinear process is resonant wave interaction, where waves must satisfy both resonances in wave numbers, but also in frequencies, right? In a set of three triads, right? Okay. Both wave numbers and frequencies. And if my Fourier space is discrete, then I miss a lot of these resonances in discrete space with respect to what I would have in continuous, in infinite box limit, right? And that's how I expect a weaker interaction in a box, right? So basically, you can think of two extreme limits here. Okay. So this limit here is where, okay, well, as a matter of fact, of course, every resonant interaction has a broadening, right? So the resonances always have a particular thickness which is bigger for bigger nonlinearities, right? So if I consider extreme cases where amplitude is so weak and the broadening is so thin that I can only cover with it one mode at a time, right? So this is very weak excitations, and I only take into account then only exact resonances, because the next one is not covered by the resonance. So there's another limit where resonance broadening covers a lot of waves in the system. Okay, and nonlinearity can still be weak in this case, right? So this broadening can be smaller than the frequency itself, right? But much bigger than the spacing of modes in Fourier space. Okay, and this is in fact the classical limit when so-called weak turbulence theory works. So weak turbulence theory, at odds with its name, cannot work for when turbulence is too weak. It has to be strong enough to cover many, many resonances. Weak turbulence theory does not work on exact resonances. It works on quasi-resonances. And that's precisely quasi-resonances that make phase randomization happening, and which results in a closure, a kinetic equation. So let me first of all consider the limit of very weak turbulence, where only exact resonances are happening. And then if you look at this equation here, right, essentially what can happen in this, what I should do in this limit, everything that has this oscillating factor present there, I should ignore, because it's so fastly oscillating, it's not going to give any cumulative contribution into the right-hand side long-time evolution. Okay?
If your turbulence, if your amplitudes are very weak.
In this case, I'm at the moment I'm considering very weak case. Yes, so this case.
I agree. But if they're really weak, then you should worry about the effect of four-wave interactions, where resonance conditions can always be satisfied. So you might be in a limit where...
well, look, you know, this particular dispersion relation is, I would totally agree with you for other systems where I lose three-wave resonances, exact resonances in this limit. Such as, for example, capillary waves on water surface. That's the case. So then I would have to go and consider four-wave interactions that would become leading process. These guys are not lost. They're still there. Okay, they're exact. So they're still leading process. They just act in a bit a different way.
Well, I mean, you might have a situation where you just pick up instead of a quasi resonance. You just pick up one contribution from the three-wave interaction. But the contribution from, there could be an infinite number of quartets that could participate in a four-wave interaction. So that effectively that's strong.
Well, as a matter of fact, you will see, let me postpone this discussion for a bit. I'll come back to that in a second. So I think I can agree with you on a lot what you're saying here in this particular aspect. So, so essentially, what I should do, I should ignore all the selected contributions. Won't go into any detail, but you know, this is physically perhaps clear what I should do. And if I do that, okay, so then what I get as a result, only terms where this oscillatory factor is exactly 1. Okay, only waves and exact resonances are left, right? And what you can see here, well, you can see two things. Well, that 3D waves are coupled through, they are slaved to the purely two-dimensional component. Okay, so you can see also that if I, you know, for k parallel equal to 0, this is a closed equation. So 2D component totally becomes totally independent of waves. Okay, and here let me come back to that question. So you see, maybe paradoxically, but this is a fully nonlinear system now. So this is not weak turbulence. So by going to this extremely weak limit, all linear terms are gone. And what is left is strong nonlinearity, including four-wave interaction and higher, all coming at the same strength. As a matter of fact, okay, the way to proceed solving this equation, I separate variables into parallel and transverse, and by substituting in here, I get for transverse component an equation which is nothing but exact two-dimensional version of RMHD equation, which is fully nonlinear. It's not a weakly nonlinear equation. Okay, so now we have strong turbulence in 2D component, whereas the three-dimensional wave component is slaved. So I first solve 2D component, and then I take an arbitrary function determined by initial conditions for parallel component, and that will be just advected around like that. So the full solution can be just represented like that.
Sorry, what is RMHD?
Reduced MHD. So essentially, this is when I take full incompressible MHD and assume that perpendicular wave numbers are much greater than parallel wave numbers. The situation of strong anisotropy to which this kind of system tend to evolve to. Now, look. Now I am able to estimate a posteriori, estimate the resonance broadening, right? I have nonlinear time associated with that process. And as a matter of fact, if, in terms of physical disturbance of magnetic field, nonlinear time is simple. As a matter of fact, it is also, if I could substitute here velocity, so it's like a Doppler shift. Essentially, wave component is moved about by the two-dimensional turbulence, it's slave to it, and therefore any frequency shift that is in it, it's a Doppler shift that is produced more or less by that motion in velocity field of by 2D turbulence, 2D vortices, right? So this is nonlinear time, and therefore I can now write the condition which I used, assumed for this description, that this nonlinear time is much less than the spacing between adjacent modes. I put here alpha and speed equal to 1, and therefore in frequency space, the spacing is just spacing between the parallel wave numbers.
Are you ignore steering force and viscosity, diffusivity?
Yes, at the moment, yes, of course.
Just ideal of MHD.
Yeah. So, so all of that it will be acting at the very short scales, you know. So I'm considering kind of inertial range dynamics. So, okay, so this condition then implies that this kind of slave to regime is going to happen under this condition. So relative disturbance of magnetic field has to be very small, right? So this is essentially, if you're thinking of numerical simulation, this is a factor, this is a resolution in the parallel to magnetic field direction, right? So if you, okay. Now consider the opposite case, and that's where this classical weak or wave turbulence theory works. So I emphasize, for this theory to work, it has to be strong enough, so the limit of infinite box in this theory is taken first, and only then weak nonlinearity limit is taken. Physically, it means many resonances moles are included within the resonant thickness. And then the result of that is well known. You get a closure for the energy spectrum, which is so-called wave kinetic equation. Right? Three-wave resonant interaction, but I emphasize these are quasi-resonances. Okay? From that, of course, we can evaluate from the right-hand side again the broadening of the resonance, inverse nonlinear time, and it's like this, right? So now notice B comes as square. Before that, it was B. So B square means that my nonlinear time is higher order. You have random phases, a lot of contributions cancel each other, and evolution comes in statistical system is slower than in deterministic. Okay, so that's a factor B squared here. And so the applicability then for this description is this. So this condition that I cover a lot of resonances is here. But of course the omega nonlinear has to be less than omega linear for nonlinearity to be weak. And this is this. Okay, exact sign here would correspond to this critical balance, as they call it, by Goldreich and Schroeder. That would be exact sign here, with additional assumption of Kolmogorov spectrum for B tilde. Now, so we have this condition, and what's interesting though, so these two conditions don't cover the intermediate range. So if I assume my intensities to be in this range, okay, then assuming any of these conditions and checking it later would result in contradiction. So what's happening? If I assume small resonance broadening, I would get the deterministic this sort of slave regime with characteristic nonlinear time given by deterministic process proportional to B. Okay, and I would see that I would in this regime violate my initial assumption. And same for and conversely for if I assume it is much broader, I would then violate it too. So the only way out is to say that in this range of parameters, omega nonlinear has to adjust itself to precisely the distance between the adjacent modes due to discreteness. Okay. So how can that happen? So this can happen in the following way. Let me call it mesoscopic MHD turbulence. So let me start forcing my system. Let me consider kind of a typical turbulence situation where I force at low wave numbers, right? And I will force with such energy injection rate that is in between of these two quantities. That's what corresponds to this intermediate regime of amplitudes. Okay. So delta parallel is just 2 pi over L parallel. So this is a distance between wave number spacing, parallel wave numbers. Alpha speed here, perpendicular wave number at which I force a parallel characteristic wave number. So I would have 2D cascade for the 2D component, k parallel equal to 0. Okay, and that would build for me a spectrum. In this particular case, 2D is MHD, right? So energy actually cascades forward, and the square magnetic potential experiences inverse cascade, right? So, but the thing is that this cascade would be at fixed rate, at the rate given by this site. So as soon as I would try to exceed this cascade, my resonance broadening would get bigger than the distance between the waves, and I would start exciting waves. My 2D turbulence, because of the resonance broadening associated with 2D turbulence, would start exciting 3-dimensional waves. And all of that excess of energy would go to waves, radiate into waves. Okay? But now I know that the waves in this regime are slaved. Okay? So they behave as a passive scalar, right? They kind of mixed about. And in passive scalars, energy doesn't cascade forward, it actually cascades backward. In this particular case, it has no way to cascade. I'm forcing it at low wave numbers. So energy will stagnate and start accumulating. Okay? It will start piling up until the level of energy, wave energy, 3-dimensional energy, at low wave numbers will reach such a scale that the resonance broadening becomes sufficient for the three-wave resonances to kick in. Okay, and then I would tip over and release as an avalanche in Fourier space the wave energy. Wave energy would spill into high wave numbers. Okay, it would spill in the high wave numbers, right? And by spilling, I would come back to low amplitude in wave component, so that the resonance broadening drops to that level where resonance is no more active. So to that critical level where the resonance broadening is just about or just slightly below the distance between the modes in Fourier space. Okay? And so this process would repeat itself, right? So I force 2-dimensional modes cascades, okay, with constant rate, trying to exceed this rate, generate waves. Waves pile up. They reach second critical value, which is here. That's where kind of wave turbulence kicks in, spills, and I go back to slate. I'm oscillating. In this intermediate regime, I'm oscillating between slaved and between wave turbulence regime. So let me put a summary here. So if I go over the range of parameters, say what is my controlling parameter here, the energy injection rate, the forcing, right? I force at low wave numbers, and consider first the situation where the forcing is low, very low, that actually the resonance broadening is extremely small. then in this case, I would have two-dimensional turbulence mode k equal to 0 evolving as purely two-dimensional turbulence with consequences, cascade, and everything, spectrum established. Wave component would immediately will be slaved and evolve as such. Now, on the other hand, if my forcing is large enough to cover many resonances, I am in a regime of random phases and kinetic equations. But there is also intermediate regime where the system can't make it mind. Okay, it will be very intermittent in Fourier space. All these fluxes will be bursty. It will be accumulating, released, accumulating, released. Right. So now I'll take questions.
Questions? See there.
You sketched a process that sounds very interesting. I'm not sure I understand it in the short time I've heard you describe it. Okay? Not sure that I understand it, but just little bits. Isn't it true that your conclusion that 3D modes, 3D waves are slave to 2D ones? Okay? That statement hinges on the fact that you use 3-wave resonance conditioning.
You see, it's a subtle point here, because easy to get confused with what people in wave turbulence say. Because if you look at the kinetic equation itself, right? So here too, this component is taken at kz equal to 0. Okay, it's not written here explicitly, but this is true.
Yeah.
Okay, so in kinetic equation, but this is not the slaving that I mean.
No, one step back.
Yes.
But
So
you made the statement that it's slave.
and this is precisely yes. So that it's not yes. It's I wouldn't call it three-wave resonance. It's
One step back. You had
Yeah.
condition for the omegas.
Yes.
For the omegas, you made
Yeah.
the
So okay. Yeah. So this kind of thing can be proven actually rigorously mathematically. That in broader context, that if you have in wave systems, right, in discrete wave systems with arbitrary dispersion relation more or less, so there's always a asymptotic regime. I think Walter Craig would be probably the person who to refer here. So there is always a very weak excitation regime where only modes with zero oscillations will be contributing. So your phase space is such that what happens is that resonant broadening is kind of like near resonances you have chaotic regions. And then
even the concept of resonance has to be defined depending on how many waves are interacting. In the sense that these are amplitude equations, not kinetic equations.
That's right.
At this level, you don't have, you only have k is equal to k1 plus k2.
Right.
But no condition among the omega. It's only when you start doing perturbation theory to different orders,
right,
that to lowest order you've written your 3-wave, the condition among the omegas. Omega 1 plus omega 2 minus omega 3, more of that less than some delta. That is already doing perturbation theory at the lowest order.
That is not, well, okay, that doesn't correspond to this.
No, next step.
Yeah, the wave turbulence. Yes, that would
be. That's the next step.
So, no, this one actually, mathematically, it is different. This regime. So essentially, mathematically, if I want to be absolutely rigorous with you, so I would take these modes plus a disturbance, and the disturbance would be oscillating function that is limited as epsilon to a certain power, and which is actually bounded. Okay, so this oscillating and not.
True. Okay.
No.
Let's take a look.
Yeah.
In the sense that this is also an amplitude equation where you drop the oscillating factor.
That's right.
Which is like, you have a whole set of terms with oscillating, non-oscillating factors, and you've decided, it's by fiat, that you've decided to keep only the non-oscillating terms.
That for the purposes of today's talk.
Yeah, yeah.
But what I'm telling you, mathematically, there is a rigorous theory about that.
Okay.
That what I decided to throw away is small as epsilon to a certain power and bounded.
And
Okay,
would
so
that be true even when, okay, there's a...
Philip, shall we continue the discussion?
Okay, we should discuss this.
Any other questions? Since Sridhar and Sergey,
Is it possible to check this theory in numerical simulations or experiments?
yes. So, and I think it's a good thing to do. And actually, I should mention that the numerical simulations, it seems to be typical, that we are in the intermediate regime. So you guys who are here numerical, tell me, okay, so if you're a computing system with external magnetic field, I mean, is that typical to get into that range? So this is parallel resolution. So of course, getting too weak, it's okay. So parallel resolution, what is it, 100 or something? Yeah. Well, mind you, you have to take only half and throw away the Ellis and arrange whatever, right? 100 realistically, right? So from 100 to 10, 100 to 1/10. This is quite, it's not an exotic range.